Hi everyone, I'm Xiaoming Zhang, and I'm a senior data scientist at Loblaw Digital. I joined Loblaw Digital from May 2019, and it's been over a year. So at Loblaw Digital, basically, I work on the recommendation, the personalization project, as well as the machine learning deployment infrastructure. In today's talk, I'm going to share our story about how we productionize our machine learning models as managed microservices. So in this talk, I'll cover the following outlines. First, I will start with our e-commerce use case at Loblaw Digital and how we ship our machine learning models, the tech stack we choose, and the workflow we follow. And also, I will talk about once we deploy multiple models, how we can do online testing to continuously monitor the model performance and to improve our models through, for example, A/B testing or multi-arm bandit testing. And I will also talk about some considerations in one of our case studies, how we build these recommendation services, like what is our design choices and what is the reasoning behind our choices. A few other considerations, including the fault tolerance, resilience, and security, and how we are trying to adopt the best practices from software engineering. So I will first talk a little bit about the background story of Loblaw Digital. So at Loblaw Digital, we focus on the e-commerce business of our company. That includes the PC Express for grocery pickup and delivery from different banners, and beauty boutique, PC Optimum, and Joe Fresh. So a little history about us. We started with a monolithic e-commerce platform about like 7 years ago. But as our business grows, this monolithic platform could no longer meet our requirements. So we are trying to pull out the core capacities for the e-commerce, including the products, cards or search, customer identity access management as a standalone services. And we're running them as the microservices in multi-tenancy Kubernetes cluster. So this is the background. And for our data science team, this microservice architecture allows us to manage our services individually within our team. And we are able to write in different languages and decouple the versions and release different components at different times and scale the components independently. And as well as like maintain the security boundaries between different services. So we support our data science team, support our business in a variety of ways. For the online shopping website, we provide operational related services, including the, for example, assortment, inventory availability, and forecasting service. We also provide personalization and recommendation services in omni channels, such as on the website, as well as the personalized email offers. So in today's talk, I will use a recommendation service as a case study to demonstrate how we ship our machine learning models as managed microservices. So like, how do we do that? First, we have the requirements as web services in our e-commerce website. It has to be performant. And we have the service level objective in terms of the latency and availability. And we also want our service want to be able to deploy new models in the future, and also to do online testing, A/B testing, or multi-bandit testing for different models. And we should be able to integrate our model deployment with our CI/CD pipeline using GitLab. So our solution is to adopt a model deployment framework built on Kubernetes. And we could implement multi-bandit tests to test the multiple models on production traffic. And by landing the Kubernetes default functionality, it supports the rolling update, canary deployment, and some naive A/B testing as well. So I'll jump straight to our tech stacks. So we are using some open source tools to help serve machine learning models on Kubernetes clusters. We use Seldon-core to wrap out the models, deploy them on the Kubernetes cluster, and expose it as a service endpoint and could be consumable by other web services. And we also leverage Istio for traffic management as well. So to understand how we adopt the Seldon-core in our Kubernetes cluster, we could logically split this infrastructure into a data plane and control plane and a data plane. In the control plane, we extended the Kubernetes by adding the operator and register the customer resource definition. So the operator, it is to tell the kube API server how make the reality match the configured resources. And it is run in the cluster as a deployment. And the CRD, that is customer resource definition, it is a controller object, which is a collection, describes a collection of Kubernetes native resources, including, for example, the pods, containers, services, and config map secrets and stuff like that. And in the data plane, we added a component called the service orchestrator to our inference graph. So this service orchestrator is basically a web server implemented in Java Spring Boot. So it forwards the traffic from the Istio proxy sidecar to all our microservice component. It calls this microservice components asynchronously, and to get the inference and send back in the response. So, and this service orchestrator, it also handles things like the payload logging, tracing, and metrics, and it exposes a metric endpoint for the Prometheus to script the metrics. So now for the workflow, so how do we deploy machine learning models using our previous tech stacks? So the first step will be the wrap the model and to create a Docker image. So basically, what we need to be included is in the model image is the model class. That's where we embed our business logic. So we could do either online inference or offline inference. For example, for the online inference, we load the model binaries, and for the offline inference, we pre-calculate the model inference result and write them into database. And in our model class, what we did is a database query. So we could have different options for the database as well. Like we use the Google Cloud Platform, so we leverage the Bigtable or data store or Cloud SQL instances. We could also wrap the filter rules. That is, we could do a very simple rule-based recommendations as well. And in the model, we also include the middleware code that is provided by the Seldon's language wrapper as a base image. It is basically the part of the web server. So the next step will be describe the deployment as a Kubernetes manifest file. So in this Kubernetes manifest file, we include things like the inference graph that is describing the logics between different microservice components. And it also includes the Kubernetes pod template spec that where we fill in which image we're gonna pull, and the relevant policies such as timeout, the retries, and also we define the environmental variables. We also specify a horizontal pod auto-scaling spec and also attach different persistent volumes, like for example, the secret volumes. And the next two steps will be deploy and monitoring. So we deploy this, we apply these Kubernetes manifest files using standardized tools, including the kubectl and Helm. And we embed this part in our GitLab CI pipeline configurations. After we deploy the model, we definitely want to know how the service performs, how the service status, for example, the request rate, latency percentiles, and like the error rates, the client-side error or server-side errors. And we also want to monitor in real time how the model performs For example, in our later multi-arm bandit test experiment, we will monitor how the reward to different models. And we can also define custom metrics that we could monitor in real time. And this whole workflow, we could continue to develop new models and continue deploy the models in our Kubernetes clusters. So now let's move to the model testing part. We can, in our current infrastructure, we can do some naive A/B testing by leveraging the Kubernetes and Istio's traffic management capacities. So in the A/B testing, we could randomly route a percentage of traffic to one model and the rest of the traffic to another model. But we can actually do better than this. We could do a more sophisticated multi-arm bandit testing. So in this multi-arm bandit testing, compared to the naive A/B testing, what we have is when we do not know which model is the best performing one, and we want to explore the models, that is the exploration region, and we want to make sure our services is having the best possible outcome. That is, we dynamically allocate the traffic to the best performing model branch. That is the exploitation stage. So in the multi-arm bandit testing scenario, we have the router component and we have the model component. So in the router component, we will do two things. One is we decide which model to route to, and what kind of reward we are going to assign to different models. So I'll jump into more details here. So in a typical multi-arm bandit testing scenario, so we will start with a set of possible actions. That is, in our case, that is different types of models. And when we take the action, choosing one of the models, it will generate an outcome. And for this outcome, it will lead to a reward, depending on our specific reward logic. So the whole idea of this multi-arm bandit experiment strategy is to find the action item, to find the action that maximize the expectation of this, to maximize the expectation of the total reward. So typically we could do two types of strategies. One is the epsilon gradient strategy. It is more easier to implement. So we have a small positive number epsilon, which is much smaller than 1. So we randomly choose one of the model branch from these actions. And for each trial, we estimate the payout rate, that is expected reward, for each of the action. And after these trials, we select the case action with the highest payout with the probability 1 minus epsilon, that is a larger probability. And meanwhile, explore other actions randomly with a smaller probability epsilon. So that's how we balance the exploration and the exploitation stage. And we could also implement a more final strategy called the Thompson sampling. So in this case, we do not know how the model performs. So we first estimate this uncertainty, use a distribution of PX. So we sample a model parameter theta from this distribution and select its action that is associated with the highest model parameter theta. And after we apply this action, we could observe the outcome and calculate the reward. Then we update the distribution by conditioning of the observation. So to implement this multi-arm bandit experiment, we have several things to consider about. One thing is to choose the routing algorithm. Basically, it's a mapping between branch values and the routing state. And we could choose either the epsilon gradient Thompson sampling, or we could implement any kind of customer routing logic in it. So we could apply some rule-based model assignment. And for the reward function, we could start with, that is, the action X yields an outcome. So this reward is generated by this outcome. We could start with some Bernoulli type of reward. So for example, if we have some recommendation services on the website and we recommend some product to the user, we could assign the reward based on if the user clicks through the product or added it to cart. And in the detailed implementations, we actually face more realistic problems. So as we are deploying our services on Kubernetes, so the best scenario we can have is a stateless service that gets the data from the environment or other stateful services. And the stateless services are easy to scale to administrator and to migrate to new versions because they are lack of state. But the reality is, it is generally not possible for us to avoid using stateless services at this time point. Why? Because we need to persist the routing state. That means if we spin up a new replica, we do not want to have it with a cold start. We wanted to get the routing state from a persistent storage or database. And another thing we need to consider about is whether or not we need the session affinity. That is, when the user try to refresh their browser, like after 5 seconds, if the search result or the recommendation result is totally different, it will lead to a bad user experience. So we need to implement the session affinity to certain circumstances. And another practical consideration is how we can construct the feedback loop. Because in the feedback loop, we need to calculate the reward based on the outcome. And we need to use this reward to update the branch values. And we need to use these branch values to update our routing state. So how can we do that? We could ideally, we want to do that in real time. For example, in our website front end, when the user add this item to cart or clicks through some items, the front end will send us some asynchronous message to our feedback endpoint, and then we could calculate the reward and send the reward to our persistent storage. And for now, what we are implementing is actually an offline reward calculation because we still need the capacity from the front end. So in this diagram, we can see that we do not have a real-time feedback loop. So we use a scheduled job to collect the web analytics data and calculate the reward and the routing state and save it to a database. And our router will pull our router will pull this branch state and the routing object from our database. This is one of our current implementation. It is not ideal, but it works. So now I will come to our case study, how we build the recommendation services on our e-commerce website. So the design part, so in our design, we try to decouple the model training and the serving pipeline. The reason we are doing this is that we could manage them orthogonally. So we can make changes to our services without breaking the entire things. So in the training pipeline, we can see that we digest the data from various sources. For example, we could digest the transaction logs like the sales receipts, product metadata from our analytical data warehouse. We could ingest our digital assets, for example, the product images from the cloud storage. And we could also, sometimes we will need to connect to our on-prem database as well. So after the data ingest step, we will do the training, inference, and post-processing jobs. Basically on the data proc cluster, it is the managed Hadoop cluster service. But so it is not necessarily that we run all of our training jobs on the Hadoop cluster. For some of our recommendation services, we are also able to use the Kubernetes GPU node pools and run distributed training jobs on that as well. So after this training, inference, and post-processing step, we use the dataproc HDFS connector to write this part of data into a GCS bucket. And we run a data pipeline job using a data flow that is a managed Apache Beam service to write this part of data to our database. That is, we use a cloud big table which is a managed NoSQL wide column database. So for different type of models, we could save to different tables. For example, here in this diagram, we have 3 different models. So for the serving pipeline, as I showed before, so we will deploy this machine learning model here at the REST API endpoint under our application namespace. And this service could be consumed by other web services, which could be deployed under another namespace in our Kubernetes cluster. And in our REST API service, we run the queries. We run the queries to different models. According to the multi-arm bandit test, we might choose to different models according to their performance. So there are several considerations on this recommendation service. So first is the fault tolerance and resilience. Because we are building a web service, we actually want to make sure this service could withstand abuse of a typical e-commerce website. So we need it to meet our requirements in terms of availability, scalability, and durability. In terms of the availability, it means that we need to implement the health check. We need to know that we need to spot whether the service is up or not, to spot the problem as early as possible. And we also need to implement functions to prevent this overload failure. This is also a joint effort between our API consumer and our side. So for the client side, they typically could implement things like the circuit breaker pattern or exponential backoffs. And in our side, we could leverage the Istio's traffic limit management feature to apply rate limiting or timeout policies. And in terms of scalability, we are leveraging the Kubernetes horizontal pod auto-scaling to spin more or less replicas to handle different web traffic volumes. And in terms of durability, currently we leverage the Google Cloud Platform's managed services to their default data replication. For example, when we are using Cloud Big Table as our database choice, it stores data in the Google file system, and provides better durability than the default 3 replicas provided by the HDFS. Another thing is, after we deploy the machine learning model as a service, we need to monitor the service state and the model performance. So this is how we pull out all these all our monitoring, logging, and learning pipeline. So here we leverage the GCP's default stack driver to monitor the custom metrics and also the container logs from our model deployment. And we also use a Grafana and Prometheus to monitor the performance and the customer metrics for our deployment as well. And also, we could integrate the PagerDuty to as a notification channel of our Grafana dashboard. So when we monitor the service metrics, and so we could set up alerting rules based on our service level objective. So for example, if the latency is above the threshold or the error rate is above the threshold, we will this will trigger alert, and we could set up the on-call schedule to maintain our service. And we are also trying to adopt some best practices from software development. In our case, we're trying to commit a better testing framework. So basically, we have this unit test, integration test, and performance test. This is done either internally or as a cross-team effort. For example, in our unit test, we definitely want to test the model class methods like the prediction methods or the route methods. And we use frameworks such as the unit test or PyTest for Python language. And for the integration test, it is done by both our side and from our API consumer. So from our side, we test the multiple microservice components, and also our the e-commerce website backend service team. They will do the integration test from their side as well. And for the performance test from our side, we typically use the low-cost distributed load testing. So basically, we spin up a low-cost workers and send out the, so we could spawn a certain number of concurrent users and send requests to our service as much as possible. So during this test, we will try to make sure we have a realistic concurrent traffic volume and concurrent users, and also a realistic cache hit and miss rate. So we could test the latency and the throughput of our service. And from our service API consumer side, they will conduct the independent performance test from their side as well. Another consideration is the security part. So it has 3 aspects we need to consider. One is the credentials. For example, that is the service account JSON case or the access tokens. For these credentials, we will save them in Vault service, and that is running on our Kubernetes cluster as well. So during our container build time or runtime, we could pull these credentials from the Vault and create a Kubernetes secret, mount them as a secret volume to our deployment pod. In terms of network, we deploy our service in a private Kubernetes cluster under a shared VPC network. We are not exposing to public internet traffic. We only enable the internal DNS record, and we also configure our gateway to accept traffic on port 443 only, so it only terminates HTTPS traffic requests. And we also leverage the ECU's security measures, security by default. So we don't need to make changes on the application code or our infrastructure. So current security measures including like the mutual TLS between for the inter-service communications, and the end user request authorization using the JSON Web tokens. And also we apply some namespace-wide authorization policy as well. So this is so far our major considerations of building this machine learning model as a managed service. And what's next? So as we already have this mature workflow, so our goal is to deploy more and more data science services to our production environment. And also we consider things like build a real-time feedback, and that involves working with the front-end team as well. And we also want to improve our extensibility in terms of both the code and the data as well. So for the data part, we are trying to build the things like the feature store to reuse the data, including like different embeddings and features. So yeah, that wraps up my presentation, and thank you for your interest. If you have any question or suggestion, feel free to send it in the chat. Okay, let me see the questions. How do you measure the reward for multi-arm bandit testing? So this is a good question. Let me go back to the this slice. So for each outcome, it will lead to a reward, and we do have we do need to specify the logic to calculate the reward. For example, if the user accepts if the user clicks through this product, we could consider this as we could consider a Bernoulli reward. That is, we add 1 to this specific branch, or we could also apply some more sophisticated reward logic. For example, it could be time decay, and also depends on what kind of product or what kind of recommendations we have made. And let me see, another question: how is to learn what has to be at real time? So another good question is this: multi-bandit strategy needs to learn over the requests, so the state is being updated in real time. Well, this depends. So as I said, as I showed in this diagram, this is actually a search rank services built from just deployed from our team. So in this one, we are not implementing a real-time reward because we do not have a capacity from the front end. So what we did is we use this web analytics data and run a data pipeline and calculate this state and reward and stuff, and deploy our router as a status service and pull this persistent state or reward or the routing from our backend persistent database. But we are trying to build a real-time feedback and reward calculation in the future. So what kind of library tools and bootstrapping implement this multi-embedded routing? So basically, we are just using a plain Python to implement this multi-embedded route logic. So can you give an example of how recommended model A and B, C differ in your model testing? So I will take this epsilon gradient and Thompson sampling as an example. So for example, we have model A and B and C. So if we are implementing epsilon gradient, so we randomly choose a model, for example, model A for this request. And after we get the feedback and calculate the reward, we could know what is the payout rate for each variant, like model A and B and C. So after some trials, we found that model A has the highest payout rate. So we could select model A with a probability of 1 minus epsilon, which is a larger number, because epsilon is a very small positive number, much smaller than 1. And for Thompson sampling, it is more sophisticated. So first, we assume 3 different distributions for model A and B and C. So after we select some action, for example, we select model A, and we sample this model parameter theta from this distribution and assume that model A gets the highest parameter theta. So we will select model A that is associated with this parameter. And after the feedback loop, we'll update the parameters of this distribution. For example, if we are using some beta distribution, we could update the 2 parameters, the alpha and beta of this distribution based on their reward. And so after we carry on this experiment, the distributions for different model A and model B and model C, their parameters are updated. So the model parameter that's sampled from this distribution will be different as well. And it is a much higher probability that the model that with better performance will be chosen. Yeah, for this epsilon gradient, in this case the epsilon is fixed. So for each in our current implementation documentation, I think. Okay, here. So is each model in its own container and has its own API endpoint? So actually in our case, because the deployment unit on the Kubernetes cluster is a pod. So in this pod, that is in one of our machine learning model deployment, we have several containers. One is the Envoy proxy from Istio that handles the inbound and outbound traffic. And we also have this service orchestrator container that is the web server provided by Seldon. And we also have three, or in our case, we have these three microservice components. That is two models, model A, model B, and the router. So this microservice component, they interact within the pod. And the pod itself, it has two external API endpoints. One is for the feedback, one is for the prediction that we get the model inference. Another endpoint is the feedback that we could send the model, for example, the reward or the branch values to this deployment. And I think, yeah, we have our colleague Anshuman in this in the chat channel as well. So this one, in this diagram, this search re-ranking services. So Anshuman could answer more questions about this one as well, because Anshuman and Joshua is the person that we work on the search re-ranking service. Yeah, I think that's all the questions. So if you have further questions, you're welcome to direct message me, or I'll also show up in our exhibition expo booth, so we could have more discussion there. And thank you for your interest.